All right, hello again, guys. So in this recording, what I'm going to do is just review the sort of instructions for this worksheet. For today, the 26th, I am just having you guys do up to number 20 on part 1 of this worksheet, which means you're going to do only covalent compounds and ionic compounds with a set charge. We will continue this worksheet. We have a bunch of practice to do, so if you want to get ahead of it, you can. This is just going to be our kind of classwork for the next couple of days. So what I also wanted to do is go through a couple of examples. The examples that I'll be looking at are numbers 1, 4, 11, and 19. I usually have you guys choose whatever looks the worst in class, but I hope I chose some examples that will provide a little bit more meaning to the different types of nomenclature and what you're looking for. I will say, I can't predict every question you guys are going to have. So please, please, please feel free to shoot me a quick question. You can post a comment or a private comment. I'll try and respond as fast as I can. I do get your notifications to my phone. So again, even if you guys have just a quick question, feel free to send it my way. So let's just remind ourselves what we're doing here. I would encourage you guys as well, have your polyatomic ion worksheet out, even have that summary slides page up. If you want to have your notes out, if you want to have the full PowerPoint, you can definitely look through it. But I think the summary slide and your polyatomic ion worksheet, that's really what you're going to need. Maybe the prefixes too. All right, so here we have it separated on this worksheet. We've got covalent compounds in our 1 through 6. We're told ionic compounds are 7 through 26. You only have to go up to 20 today. And then 27 through 38 are ionic compounds. And you'll notice down here on the bottom section of this worksheet, we have Roman numerals. So tomorrow, I'll give some more practice. We'll take a look at doing ionic compounds without a set charge. But for today, I want you guys just to do 1 through 20. So with covalent compounds, we're going to be looking at prefixes, which is also why when you look at the nomenclature like 1, 2, and 3, you get these difluoride, hexafluoride, dioxide, these prefixes in your nomenclature. You will only see prefixes in covalent compounds. So here on this worksheet, it is kind of labeled for you. You're told they are covalent compounds. If you scroll down to page 2 of this document, you will notice that I've mixed them all up. So I mixed all the covalent, ionic with a set charge. They're all together. So we're working towards that goal of being able to look at something, whether it's in the nomenclature form or in the chemical formula form, and know if it is ionic with a set charge, without a set charge, or covalent. So we'll get there, but for now we're just doing some introductory practice. So let's start looking at our examples here. The first example, number 1, oxygen difluoride. So for oxygen difluoride, we are given the nomenclature and we need to create the formula for it. So what we'll note is in a covalent compound, you are told the prefixes, and those indicate the number of atoms of each substance. Oxygen doesn't have a prefix on it, which means that we must only have one oxygen. We will use the prefix mono on any second element. So for example, here we have difluoride. If we only had one, we would be forced to say monofluoride. You don't have to say mono for your first element, so for oxygen in this case. The reason why is it just ends up being redundant. Even if you look at examples 1, 2, and 3, they all are going to have one atom of the first element. So if we always had to state mono, we would say mono this, mono that. Like it would be super, super redundant. Like many chemical formulas would have mono in front of them. So it is inferred that if you don't have any prefix at all, it must just be mono. So we have one oxygen atom. Now we have difluoride. So it's telling you you have the element of fluorine. And di is the prefix for 2. So we must have 2 atoms of fluorine. So our chemical formula is OF2. Now, if you need to take a second look at your prefixes, I encourage you to do so. We won't be using the prefix bi for 2. think I said it in class, but again, bi refers to one or the other versus di refers to the number 2. Other common prefixes we will see in number 4, which is our next example. All right, so for number 4, SiF4, we're given the chemical formula, and now we have to give the nomenclature for this. So we see that it's Si, that is silicon. So silicon. We do have only one atom of silicon. We're not going to say monosilicon. Again, that would be super redundant. We would have mono whatever for tons and tons and tons of covalent nomenclature. So we just say silicon, but we do absolutely have to tell our reader about how many fluorines we have. Now, one other thing I didn't touch on in number 1, and maybe I should have, is about the ending here. So for fluorine, the element, we're going to drop the ending. So fluorine is going to become fluoride. We have 4 of them, so we're going to use the prefix tetra. We can't use the prefix quad. We're going to use the prefix tetra in chemistry. So we're going to say it's tetrafluoride. All right, so for tetrafluoride, the thing I wanted to point out to you, if you saw only the nomenclature, like let's say you didn't see the chemical formula of SiF4 and you just had silicon tetrafluoride, you can always work back. You can always say, oh, silicon, I don't have a prefix, I must have 1. Tetrafluoride, fluoride, that IDE ending is telling me that it is the elemental version. The prefix is telling me that I must have this covalent compound. I've got 4 of these fluoride atoms in the compound. So we can always work back and say with certainty that this chemical formula is this nomenclature and vice versa, and there's only one option for it. Okay. All right, moving right along here to some ionic examples. Number 11 is ammonium phosphate. Now, I like this one. We've got 2 polyatomic ions in them. Ammonium, you guys are going to have to memorize ammonium. It's the only positive polyatomic ion, but what I would say is oftentimes I have kids looking on the periodic table and they're like, I can't find ammonium. Where's ammonium? So again, it's tough when you are faced with something and you're like, oh, I don't really have it in my memory banks yet. That's why we're doing a lot of practice. But ammonium is NH4 plus. Phosphate should give you a hint, though. So that ATE ending, that is a polyatomic ion ending. So phosphate, that is PO4 3 minus. So you should look at that ATE ending and say, that's a polyatomic ion. If you had something different, let's say a different example, ammonium phosphide, an IDE ending. Then we would say if you had an IDE ending, it would not be the polyatomic ion, it would just be the element. So you guys will definitely see that in these examples 1 through 20 on this worksheet, as well as the rest of the examples when we get to them. So pay attention whether if something is phosphate, phosphite, phosphide. Again, we'll see it in our next example in 19, but for this one, that ATE should stand out to you. All right, so to create a neutral ionic compound for ammonium phosphate to have the correct chemical formula, we recognize that ammonium has a positive 1, phosphate has a negative 3. We need to create a neutral compound, so they have to have a cation and anion that cancel each other out. We're going to do this by creating a negative 3 on the phosphate side. We already have it. And a positive 3 on the ammonium side. In order to do this, we need 3 of our ammonium ions, or ammonium polyatomic ions. So what this is going to look like is parentheses NH4, end parentheses 3, PO4. So you should have 3 of your ammoniums. That gives you a total of plus 3 on your cation side. That balances out with your 1 negative 3 charged phosphate. And as a reminder, when you guys are creating these chemical formulas, you should never have a charge in your ionic compounds. We recognize they're neutral overall, so you shouldn't have any positives or negatives hanging around in your formulas. You'll notice that if you look over to your right and you see all these examples, that 17 through 26 examples, none of them have charges in them. All right, so the last example, and then I'll stop bothering you. Number 19, Mg3N2. So for this, we have an ionic compound. We know it's ionic, not just because it's told to us on the page, but we have magnesium, which is an alkali earth metal. We know magnesium is Mg2 plus. Nitrogen, we know nitrogen has a set 3 minus charge. It is 3 away from the noble gases, so when it forms its ion, it will always be M3 minus. So that's why we have 3 magnesium atoms and 2 nitrogen atoms, because their charges are not equal to each other. So although their charges aren't equal to each other, and we have this formula of Mg3N2, magnesium and nitrogen as ions have set charges. So you don't have to tell your reader, and in fact you never would, you don't have to tell your reader about how many atoms you have, like we did in covalent, because ionic compounds only have one possibility. They're only ever going to come together in that least common multiple for their neutral ionic compound overall. So to name this, we're just going to name it magnesium nitride. I will note, though, the nitrogen having that IDE ending, it could not be magnesium nitrogen. We have to name it as magnesium nitride. But again, other incorrect things, you would not name this like trimagnesium dinitride. Again, it would be super redundant because there's only one way that a magnesium and a nitrogen atom can come together. It has to be Mg3N2. So all you need to tell your reader is it's magnesium nitride, and every other chemist will know, oh, that's Mg3N2. All right, so I'm going to post a picture of what I was writing here as we went through these practice examples. I hope this helps. Do your best to get through 1 through 20. Submit your answers to me however you like, and we will do some more practice tomorrow.